What if every light signal you send also comes back from the future? That's the bold idea behind the Wheeler-Feynman Absorber Theory. Instead of an electron simply emitting a one-way pulse of light or radio, X-rays, etc., it partners with every future charge in the universe. When you accelerate an electron, it emits half its field forward in time and half backward. Future charges absorb the forward pulse and send a matching signal back in time. They're advanced waves so that only the familiar forward in time radiation survives. Why introduce backward in time waves at all? In the classical electrodynamics, an accelerating charge seems to push on itself, leading to infinite self-forces and unphysical runaway solutions. Wheeler and Feynman realized that if every emitted field truly ends up in an absorber somewhere, stars, dust, your radio antenna, then the self-action cancels out. The electron never feels its own field. It only interacts with the fields reflected back by others. This neat trick banishes infinities by relying on perfect cosmic bookkeeping. How can something from the future influence the past? It sounds like science fiction, but in the math of Maxwell's equations, advanced solutions, waves traveling backward in time, are just as valid as retarded ones. Normally, we throw out the advanced solutions to preserve causality, effects after causes. Wheeler and Feynman kept both, then showed that the universe's absorbers conspire to cancel all backward ripples at the emission point, leaving only ordinary causal radiation. It's like two synchronized swimmers whose moves mirror each other so precisely you only see one performance. Can we spot these advanced waves in real life? Directly, no advanced fields cancel before they reach us, but we see hints in clever lab setups. In certain metamaterials and electronic circuits, carefully timed feedback loops create pre-responses, where the system seems to react before the trigger hits. These aren't true time reversals, but they show that wave-based systems can flirt with advanced-type behavior if you choreograph absorbers just right. What everyday example helps make sense of it? Think of a long telephone call. You speak, your voice travels through wires, and the far end listener's microphone feeds back into your earphones. You don't hear your own voice until it's processed and sent back. Similarly, an electron's field only lands on another charge and returns a half replay. So the electron detects radiation only when it's absorbed elsewhere. Does this theory really describe our universe? And it works beautifully on paper if you assume a perfect absorber cosmos. Every photon eventually meets a matching charge, but our expanding, partly empty universe may not soak up every stray wave, and extending absorber ideas into quantum mechanics bumps into puzzles about entanglement and the measurement collapse. Why should curious beginners care? Because absorber theory challenges our most basic notion of cause and effect. It hints that the future might be as active in shaping events as the past, and that every act of emission is a handshake spanning time itself. Even if nature only approximates this symmetry, exploring it pushes the frontier of how we understand radiation, information, and the deep arrow of time. The Wheeler-Feynman Absorber Theory posits that electromagnetic interactions involve both retarded, forward in time, and advanced, backward in time waves, with emitters and absorbers jointly determining radiation. When a charge accelerates, it sends out a half-retarded and half-advanced field. The advanced component is canceled, except where future absorbers respond, completing the interaction. This time-symmetric view removes the need for a self-force on the emitter by attributing radiation reaction to the combined response of all absorbers in the universe. It challenges the standard notion that fields propagate only forward in time. An electron's acceleration in an antenna emits fields that are only fully realized when the surrounding circuit and ambient charges absorb the radiation, generating the observed damping force. It is like whispering a secret into a cave. Your voice travels forward, but an echo from the cave walls sends information back to you almost simultaneously shaping your original whisper. Standard electrodynamics uses purely retarded Green's functions. Signals travel from past sources to future fields. The absorber theory, instead, employs the symmetric Green's function, combining retarded and advanced solutions. The retarded part carries energy outward. The advanced part carries pre-responses from future absorbers back to the emitter. Recognizing this distinction reframes radiation as a two-way handshake across time rather than a one-way broadcast. In classical theory, a radio antenna sends signals that never know about the receiver. In absorber theory, the receiver's presence in the future is integral to the emission process itself. It is like sending a letter that only gets written if the recipient sends confirmation ahead in time. So the act of writing presupposes a reply. At the microscopic level, each accelerating charge generates both forward and backward traveling field components. These components superimpose with fields from all other charges in the absorber ensemble. The advanced fields from absorbers converge on the emitter at precisely the moment of acceleration, providing the radiation reaction force without self-interaction divergences. Thus, the microscopic origin of damping lies in coherent interference of fields from the entire universe. In a cloud chamber, the path of an ionizing particle is influenced by both its past accelerations and the future absorption of its fields by nearby gas atoms. It is like walking on a trampoline that only sags under your step because future spectators push down from above at the same instant, creating the expected dip. The theory requires a perfect absorber condition. All retarded energy is eventually absorbed and no stray radiation escapes to infinity. This global boundary condition enforces that the advanced waves precisely cancel unwanted self-fields. Mathematically, one imposes that the sum of all advanced responses at any emitter equals the negative of its own advanced field, leaving only the physical retarded field. The mechanism thus relies on the universe acting as an ideal sink for radiation. In practice, dense conducting walls, or cosmic background charges, serve as near-ideal absorbers that enforce the boundary condition locally. It is like shouting in a perfectly sound-deadening chamber. Every sound wave you produce is immediately absorbed by the walls, so you never hear an echo. Retarded waves convey causal influence from a source to its future environment, while advanced waves carry the absorber's feedback back to the source. Their half-and-half combination ensures energy is conserved and radiation reaction emerges naturally. Advanced waves alone are not physically observed because they cancel out globally except in their role shaping emission. Together, they form a time-symmetric interaction kernel that underlies electromagnetic forces. Two charged particles exchanging photons do so through a superposition where each perceives both the other's past and future accelerations. It is like two dancers synchronizing steps by both sending and receiving cues into the future as well as the past, maintaining perfect harmony. By avoiding self-fields, absorber theory circumvents the infinite self-energy problem of point charges in classical electrodynamics. The nonlinear requirement that all absorbers respond collectively removes singularities associated with a charge acting on itself. Radiation reaction appears as a finite term derived from the absorber sum, rather than from ad hoc renormalization. This elegant mechanism solves long-standing divergence issues in a time-symmetric framework. Detailed calculations show that the notorious Abraham-Lorentz cell-force formula emerges without infinities when absorber boundary conditions are enforced. It is like dissolving a knot by tugging on all strands simultaneously, rather than pulling on the single loop that tightens when you tug it alone. Although it incorporates backward in time components, absorber theory preserves overall causality because advanced effects only appear when matched by future absorbers. In quantum versions, the transactional interpretation builds on this, describing emitter-absorber transactions as handshakes via offer and confirmation waves. This offers a physical picture of wave function collapse and entanglement consistent with standard prediction. Thus, absorber theory informs both classical and quantum understandings of causality. In the transactional interpretation, an electron's emission of a photon involves an offer wave forward in time and a confirmation wave backward in time from the detector. It is like sending an invitation, offer, and receiving a RSVP confirmation before the event, making the gathering happen only by mutual agreement across time. Testing absorber theory directly is difficult because advanced waves are never observed in isolation. They always cancel except in reaction forces. Any deviation from perfect absorption at cosmic scales could introduce measurable anomalies, but such residuals are exceedingly small. Precision experiments in low-loss cavities or with controlled absorber distributions may someday reveal subtle effects. For now, the theory remains empirically equivalent to standard electrodynamics in almost all regimes. Proposals to detect advanced effects involve precision laser interferometry in near-perfect vacuum chambers, but none have observed unambiguous backward signals. It is like trying to detect a whisper in a perfectly silent room. You need ultra-sensitive equipment, yet the whisper vanishes as soon as you strain your ear. The absorber framework inspires research into time-symmetric formulations of other forces and into novel quantum interpretations that resolve measurement puzzles. Advances in metamaterials and engineered absorber environments may one day allow controlled tests of absorber boundary conditions. Exploring absorber principles could yield new insights into radiation control, energy harvesting, and causality in complex systems. Ultimately, Wheeler-Feynman theory challenges us to rethink the flow of time in fundamental interactions. Synthetic absorber arrays are being designed to manipulate radiation reaction forces on microantennas, testing absorber theory predictions at small scales. It is like crafting a custom echo chamber so perfect that you can watch how your own voice fades out in unexpected ways, revealing hidden acoustic laws.